Okay, welcome everyone to this webinar. The today presentation is related to geothermal modeling using FEFLOW. So we have a great number of participants, more than 60 interested in modeling geothermal applications with FEFLOW. For those who are new to this series of webinars, so we have every month a different topic related to numerical modeling using FEFLOW. Today or this month is related to geothermal. For those who doesn't know me, my name is Carlos Rivera. I'm located in Berlin, Germany, and I work in DHI as a global product specialist. So I'm responsible for FEFLOW as a product at the DHI group level. Okay, so the agenda today is we will start with some announcements. So then a quick overview about FEFLOW, because looking at the names, there are several participants who are new to the software. So we will discuss about geothermal applications using FEFLOW, live demonstration. So if you really want to start modeling geothermal systems with FEFLOW, I would really recommend you to go through our training website. So we have the Academy by DHI. This is our training program in DHI. And we have a number of free accessible training courses, what we call self-paced training courses. So usually you will spend between 2 and 3 hours of your time per course to get an overview of different topics about groundwater modeling or geothermal modeling. So I would recommend you, if you're starting with FEFLOW, to take a look in these 3 courses. So we have an introductory course about FEFLOW, and then we have 2 courses which are interconnected. So one is related to open loop systems, and the second is related to closed loop systems. So the courses are accessible for free. You just need to register, and you will get access to the training course and material. Secondly, we will be offering an in-person training course about geothermal modeling from shallow down to deep geothermal reservoirs using FEFLOW here in Berlin, Germany, from the 20th to the 22nd of November this year. So we still have some seats left. If you are in Europe or you would like to visit Berlin and learn about FEFLOW and geothermal modeling, so please register. So that website for the registration is the one here, and you will also get more hints in the follow-up email that you will receive after the webinar. And with this, I would like to jump into the topic of today's presentation, which is FEFLOW. For those ones new to modeling and new to FEFLOW, so FEFLOW is a finite element software already old and being capable to simulate a multitude of different processes from groundwater and geothermal reservoirs involving flow, mass, and heat transport, and you can also interconnect these different processes. FEFLOW is an old software, already exists in the late 70s, and from the very beginning, we have always implemented mass transport or heat transport. The software is continuously being developed by DHI, so we will have later this November the release of FEFLOW A1, which, by the way, is bringing a lot of features related to geothermal modeling. FEFLOW is a software easy to use, intuitive, but at the same time to model very complex surface processes. So you can build in a couple of minutes a box model, but you can also build several square kilometers regional model for your geothermal projects. FEFLOW comes with multiple processes for flow, variable saturated conditions, contaminant transport, heat transport. If we try to connect this into the topic of geothermal, so you might want to maybe simulate flow of mass and heat transport if you have a thermohaline system. You can also introduce density affected flow if you are heating up the system. So you might want to modify the density, the viscosity, the expansion of the fluid. But maybe there is also some geochemical reactions that you would like to incorporate into your geothermal project. So that is also supported by FEFLOW. Our philosophy is that we have everything in one. So for simple or complex, for multiple scales, so we can easily build local and regional models. And you have one single package, so you don't need to add additional modules or packages for doing different things. So you learn one single interface, and this interface will allow you to do all the different modeling processes. The interface allows you to set up the model, run the simulations, do some results analysis, and everything comes in one single file format. It's .fem, and for the results, it's a .file format. The interface gives you a number of tips and tips, and you can also personalize and customize depending on your needs. Here is where we start getting more involved into the example of geothermal modeling, what I will discuss later. So in some cases, when we are working in shallow geothermal, so we might want to have simple models in terms of meshes, so we can build a FEFLOW model or our domains using some 3D representation and geological representation following some layers. So you can build the discretization in 2D and then later extend the model as 3D. If you are maybe working in the sector of deep geothermal or middle depth geothermal applications, so you might want to incorporate several or complex geological or reservoir structures like layers or faults or fracture systems or karst systems. So these can be also represented very well with a technology that we have been working since already 2015. Is a technology for creating an extraction 3D meshes in FEFLOW. So you can work with geological software. So LeakFlow, for example, is a very common software used within our community. Prepare the geology, import directly the geology here, and then FEFLOW will take the inputs, create a 3D domain based on full extraction meshes, which will honor the structures that are on the complexity of the systems. This approach will also allow you to incorporate inclined boreholes, complex geometrical geometries, which you require for modeling this case. You have done the model, so then you would like to maybe do some sensitivity analysis, or maybe you have information about the geothermal response test. You can work with an interface called FEPES, FEFLOW Parameter Estimation. It's an interface that comes directly with FEFLOW, with every single license and installation packages. And this interface allows you to either calibrate a model or do some sensitivity and uncertainty analysis. Behind the scenes, we use a technology called PES, parameter estimation, which is a tool or software already existing more than 20, 25 years and developed by John Doherty in Australia. One of our major components in FEFLOW is the visualization. So you can visualize basically everything that you are doing. So during the simulation, pre or post the simulation. In 2D or in 3D, you can just draw cross sections, visualize temperature profile distributions, maybe just take some points and then check what is the temperature distribution in a specific location, for example, in the well. Few examples about this visualization. In this case, we are looking for conductivity distributions. Since all of us needs to work with a number of file formats, we are working a lot on this, and in the release even coming now, we will support new versions of AutoCAD, DW files, and others, which will allow you to incorporate easily your data into FEFLOW. We support most of the file formats in 2D and 3D available in the industry. And depending on the data, what is the data format that you have, we will also allow you a number of regionalization methods or interpolation methods. So you can, for example, have points for representing the different geological units, and you can use FEFLOW interpolation methods to get a full structure of the system. For those who knows a little bit of Python or C++, we have a very powerful open interface, programming interface, which allow you to automatize many of the workflows that you have in FEFLOW. This interface is will be also extended in some weeks. For the first time, we will be able to build entirely 3D models without opening the graphical interface. So we have now adding possibilities to call mesh generators, to create conceptual models outside the FEFLOW graphical interface, but through the Python programming interface. Let's concentrate in today's presentation, which is about geothermal modeling. But before we go into the details, so we need to ask a number of questions. So why do we really want to even model in this? So typical answers, why do you use FEFLOW in this context is for estimating the feasibility of a geothermal installation. So you would like to install the system for a number of years, 20, 25, or even more years. So you want to be able to understand whether it's feasible or not. And what is the efficiency of the system? So if you are designing, so you would like to understand what is the positioning of the wells. So what are the number of maybe portable heat exchangers if you are doing low enthalpy geothermal? So you want to estimate the number of wells that you require for the demand. Maybe you want to optimize those wells, so when to pump, when not to pump, where the wells has to be located, or a combination of these different factors. And obviously, last but not least, we are interested to know what is the potential impact that we are doing on the subsurface environment due to regulations. So we are asked to demonstrate there is no negative impact in the subsurface. So we can use the simulations for understanding this. So you might not want to minimize the temperature in the aquifer or in the reservoirs, depending on what is required or requested by the different regulators. And also very important, which is coming quite often in the case of shallow geothermal models, especially here in Europe, we see more and more utilization of geothermal systems. So there is no point where we are competing or infrastructure and competing against others, but it might be some cases there is in the area where you would like to implement the geothermal systems. There might be some existing installations, so you would like to understand whether the changes that you are doing into the reservoir are contained, whether the plots or whether the area that you are interested in. FEFLOW will allow you to model a number of different systems on near surface, or better say low enthalpy systems, with typical depths less than 400 meters. You can have a number of boreholes working at that depth, but we also have possibilities to go even deeper. So there are some models out there and also a number of publications using FEFLOW in several kilometers. So here in Germany, so because we are in the Molas Basin, there are a number of papers or research institutes, universities, but also research centers investigating the use of geothermal systems, or use of geothermal deep applications in the Molas reservoir. So if you're interested, I can provide you some publications. We can also distinguish the geothermal systems by operation time, and this is also something supported by FEFLOW. So we have the possibility to introduce open loop systems where you have a production and injection well. You can have a number of wells doing these operations. And we have also implementation of closed loop systems using a special boundary condition where we call borehole heat exchanger. In this second case, there will not be advective transport, so there will be no contact with the groundwater flow. If it's shallow geothermal, it will be basically conductive transport happening in the system. So how you can use FEFLOW for these different applications? Sometimes you are working in heating, sometimes you're working in cooling and heating, so you can apply these different changes on the load by using time series in FEFLOW. So we have a flexible time series editor where you can test the resolution of your time series. This could go from hourly, daily, monthly, or yearly resolution. So it's up to you. And the software will use this time resolution for calculating the flow. This is needed, and the heat transport. So you can import all this information to different external files. You can assign it quite easily. So we have a well manager which is capable to locate all this information, all the number of wells in one graphical interface. So you can easily see how many wells you have and what is the potential connection between them. Talking about closed loop systems, so these are called in FEFLOW borehole heat exchangers. So we have multiple ways to model. So from the most simplistic, where you define the net energy withdrawal or injection, so you say how many joules per day you have per different nodes. And then FEFLOW will basically simulate the propagation of this heat plume or cold plume, depending on the case. We have a more elaborated representation where we have a 1D representation of a borehole heat exchanger, but inside you can still say that you have different geometrical cross sections. So the FEFLOW internally will calculate the temperature distribution and exchange between the different pipes. Or you have approach which is less common use, but is still possible to do, where you have a fully discretized system, where you see here a typical double U shape, where the pipes or the inlet and outlet pipes and the grouts and the wall thickness of the pipes are discretized, so they are part of the mesh, and FEFLOW is able to calculate the temperature in any location in this geometry. So that is less used because it requires a lot of elements and the calculation time might easily increase. So we focus basically on most of our users work with this BHE, borehole heat exchange special boundary, which comes with an editor, and this editor gives you possibilities to define the geometry, which we have 4 default geometries: annular inlet, center inlet, single U shape or double U shape. This geometry is persistent through the entire depth. We are looking now currently possibilities to change the geometry over depths. It's not available yet, but it's going to come very soon. We'll also use different methods for calculating the heat transfer coefficient. So you can say FEFLOW compute this for us, and then using the geometrical information and the flow information available to the pipes, FEFLOW will calculate these heat transfer coefficients. Or maybe you have done a geothermal response test, so you can import your resistance or your results of the test directly into the graphical interface, and FEFLOW is going to use this information directly for the calculation. The interface is quite nice because you easily can see the distance or all the changes that you applied. So if you modify the distance between the pipes or the thickness, you get automatically feedback on this geometry. When you run the problem or the simulations, depending on the number of BHEs, you get a set of charts. So typically you will get these two if you have at least one borehole heat exchanger. You have an inlet distribution, an outlet distribution, and a grout, where you have here depths or lengths if you are modeling the system inclined. So we will track the temperature along the length of the BHE, and you have obviously temperature here. Since you want to look whether it's possible or feasible to do or carry out these installations for the given energy demands, so we give you a quick overview of the changes of T over time for the inlet and outlet pipes. So this is actually a bad example where we immediately see a drop of the temperature after starting the operations. If that's the case, so what you obviously need is to have a number of additional boreholes to compensate or to distribute the needs of the energy in the system. For that, FEFLOW comes with a so-called borehole heat exchanger rates or interconnector editor, where you can have any number of boreholes, and these boreholes can be connected either in serial or in parallel, or a combination of these both. So the interface looks like this. It's quite simple. You can just need to connect manually. In the case of you have many boreholes, we have been seeing that there are typically now 100 boreholes, so more than 50 boreholes, so that the interface is a bit, it's not any more easy to do it manually. For that, we have recently developed the possibility to just select all the boreholes and say, I want to connect them in parallel, and FEFLOW can just do that in 1-2 seconds, straightforward. So if you're modeling this, you will expect to see such a results where you have temperature distributions through the different boreholes, and you can investigate what is the variability of T in space, but also in time. Moreover, since I was mentioning before that we have different ways of visualizing these results, so you can look the temperature distributions from the top view or from a view, what we call a slice view, which is basically cutting on the plane direction the model domain in 3D. In this example, we have two boreholes, so two systems, an open loop, we have injection and pumping, and we have a closed loop. So this example that I'm going to show later in the live demonstration. So we can nicely see here what is the decrease of temperature because we start injecting cold water back into the system, and there is a groundwater flow in which is going in the direction of the two geothermal systems. So we can see the propagation of the cold plumes in the direction of the closed loop system, which eventually is going to cool the system, the second system, after X number of years. So you can test these different hypotheses or verify the location of your wells by simply doing cross-section analysis or looking horizontally the distribution of temperature, but also velocities if you're interested. By the way, velocities of FEFLOW give you, even before you calculate the heat transport, the possibility to just do a simple particle tracking or streamline calculation, where you can identify potential travel times between one well to the other. What we see here is we have injection well and we have a production well. So I'm running from the production well backward streamlines, which will tell me how much time does it takes to arrive from the injection well to the production well. In this case, which is very exaggerated, it takes about 120 days to travel from this point to this point here downward. So you can estimate these times and then see what is worth it to have the boreholes at these locations, or maybe you will need to modify to fulfill your modeling objectives or your project objectives. So let's change now the topic, and we start talking about deep geothermal information. So a major reason why to choose FEFLOW in this aspect, I have seen a number now of questions, people asking different softwares or codes. There are a number of codes where you can model geothermal, deep geothermal systems. But I believe our major advantage is the possibility to incorporate details of the reservoir or the structural reservoir into FEFLOW. So we solve finite elements methods, and this allows us to accommodate to any potential complex geometry, where you can include different faults, or you can include different structures, like wells, faults, inclined boreholes, etc., like these ones here. The second advantage is that you have a very good way of discretizing around the area of interest. So if I will be focusing in this area, I want to have most of my finite elements located here to be able to capture all the different processes in detail. In areas which are apart from the interest, but I still not, I need to model because I would like to investigate the impact at the regional scale, so I could use large elements for the calculations. This is another example about complex geometries. This is an old FEFLOW model developed a number of years by DHI, where we test the interoperability of geological software with FEFLOW. So you can nicely see here the complexity of the different layers and bending of different surfaces and the incorporation of the faults or displayings of the layers. So this is the technology which exists since many, many years, and nowadays with 3D structure meshes is even easier to incorporate these geometries. Deep geothermal applications, so that's a box example that I usually take for demonstrating what is the purposes of this. Okay, that was too fast. So we have two boreholes, doublets. We are injecting some cold plumes deep underground. So the model has a 5 by 5 by 5 kilometers size. And we investigate the propagation of the cold plume in this in this depth location of the system. Since we are talking about different temperatures, different physical processes, so the so-called equation of states might change under these circumstances. So we could incorporate variable fluid density and variable fluid viscosity depending on the cases. So it's an optional feature. The user needs to know whether it's relevant for the application or for the project, and if so, needs to activate the possibility to calculate changes in density and also in viscosity. Okay, so a number of additional features which I'm not mentioning here because of time is sometimes in these projects also interesting to evaluate what is the geochemical impact to the deep geothermal reservoirs, because we are either changing the local equilibrium because of the changes of pressure, but also changes of temperature. So the geochemistry might also be modified. So we have the possibilities to do simple kinetic reactions within FEFLOW, or do advanced geochemical calculations with some module, what we call FEFLOW PyChem, which allow us to couple FEFLOW simulator with FRIXIS reactive transport simulator from the United States Geological Survey. And with this, you can easily calculate dissolution and precipitation processes around the workflow. So you want to see whether around the area and precipitating maybe calcite or dissoluting any mineral that could be around the location of the system. Going more to different topics, so with technology or ways how geothermal systems are installed is changing and changing more because of the demand. So sometimes there is no space, so we need to make inclined boreholes. Sometimes there is already a facility, like in this case, a tunnel. So we'd like to use what is there to apply or to install a system. So this is an example of energy diaphragm walls installed in a tunnel, which was simulated with FEFLOW, so that you can nicely see the geometry and complexity of the different pipes. And there's a publication here from Fraud in 2010, which shows the way how this has been modeled. And that's the example of the FEFLOW model, including the geometry of the pipe. So it's not everything incorporated, but only the major structures are part of the model. And you can see here the model does not have continuity in the layers, so we have a fully unstructured mesh which accommodates to the 3D polylines representing the pipes around the different tunnel walls. FEFLOW comes with a number of tools as well. Some of the tools are designed for us, for geothermal purposes, but there are also some tools designed for different users. This can be Python scripts, but it could be also libraries or compiled libraries or DLLs. One of them is called the Open Loop plugin, which is distributed for free with the FEFLOW software, which allow you to optimize or to test multiple configurations of open loop systems, where you can pass what is the COP, the coefficient of performance, and then what are your limits for injection temperature, and so minimum and maximum, what is the maximum flow rate allowed, and this is going to calculate whether it's possible or no to have the efficiency that you are asking for. Moving in another direction, FEFLOW comes with a solution for modeling freezing and thawing conditions, which might not be always necessary in this type of projects, but I would like to mention. So that's too fast. Small video, which is not really related to geothermal modeling, is mainly a geotechnical project where liquid nitrogen is injected in the undergrounds, and we are modeling freezing conditions or underground freezing. You can see that this area is frozen, and these little lines are flow velocity vectors. So basically, when the material is frozen, FEFLOW changes hydraulic and thermal properties. In terms of the hydraulic properties, you want to reduce the hydraulic conductivity to a value close to 0, and it's going to also reduce the porosity. So the flow Also, what is happening hydraulically is creating a flow barrier here, so that the vectors of velocity will just basically go around the different walls of this system. In the case of voltage heat exchanges, again, so you could ask a significant amount of energy in one single borehole or in several, which could drop the temperature drastically. So you might want to simulate effects of ice formation in the boreholes, which is not a very uncommon case. So you can model this with FEFLOW too. Yes, and with this, I would like to jump into the live demonstration. For the live demonstration, I have prepared two models. So we don't have enough time for setting up the entire model. I will show a few things about the model. And since I see a number of common faces and names, so I will also open a version that we are gonna release soon in FEFLOW, where you can take a look what is coming in terms of geothermal features. So this is example which we typically use for our training. So we have here a 3D model, and this 3D model looks like this. So has a number of properties, has 3 aquifers. We solve flow and heat transport. So one nice feature recently introduced and is available now is called Well Manager, where you can see directly the number of wells. And when we build these widgets into the graphical interface, it was with intention to see all the types of well in one location. So you can have multi-layer wells, which is a fully penetrating well, but you can also have nodal-based wells, which well-BC is called in FEFLOW, where you have one point and you either inject or pump from that location. You can also see directly in this interface borehole heat exchanges, so all the information available here. Okay, so we have here 2 wells, so injection and extraction or production well. There is a time series. Somebody before the training was asking me whether it's possible to use time series in FEFLOW for these applications. Yes, it's quite straightforward. You need to go to the edits, time series, import or write your time series as you want. And here we have a pumping and injection time series. So whatever we pump, we return it back to into the aquifer in the same amount. So it's just the same absolute values, only changing the algebraic sign here. Okay, for this open loop system, we use a technology called open loop plugin, which is quite old. And basically the plugin allows you to create doublets or triplets. And this will be connected with another time series, in this case, this one, which tells what is the delta of temperature of between the production and injection wells. So in this case, it's telling me that the first 120 days, whatever I pump out from the production well, let's say I have 10 degrees been pumping out, I'm gonna return it back into the system with -3, so with 7 degrees. You get this information from your energy demand and from the seasonality that you would like to implement in the model. So winter or summer, whether you are using the system for heating or cooling, this is something that you can implement directly. And the system is a cyclic time series, so we run the model for a number of years, but we only provide data for 365 days. So FEFLOW is gonna repeat every time the time series once again and again. Okay, so that's our temperature distributions, and this is the location of the wells. So the wells are changing in different, are going in different slices, what we call, and if we quickly run the simulations, I need to save it, then I can say that there is something start happening. So this is our injection well, so we start with entire model domain of 10 Celsius degrees, and we start now adding cold water, because remember, in the first period of the modeling is -3, so we are basically injecting about 7 degrees back into the system. The flow direction in this case goes from the left of my screen to the upper right corner of my screen. So we could see we will gonna see the propagation of this plume following the flow direction. And the two wells, they have a distance approx of 125 meters. So we can also investigate with FEFLOW whether it's gonna cold plume come to the production well. You can easily see the changes of temperature by looking the average temperature history, where you see two lines. So one in blue is the injection well, and the one B in red is the production. So we need to wait a few seconds and that we change the cycle of the time series, that you can see how the response of the well. So this is the average value of temperature to all the multiple nodes where the system is, where the wells are located. So now we have a cool system area, and we are heating up again back with about 12 or 13 degrees Celsius. And if you see, I will make this a little bit thicker. It's probably not possible to see. Now you see the lines. So we have the change on our 10 series. So we are heating up. So we are the aquifer is at the beginning is with 10. If the system is working, so our production well now is 10, approx 10, less than 10. If we have enough separation between the two boreholes, hopefully we are not going to decrease the temperature of the production well. So this is something that we can use and visualize in FEFLOW. Okay, so I'm going to stop the simulation here, and I will open a file which will allow me to demonstrate the use of closed loop systems into FEFLOW. It's the same model. This time we incorporate, let's put this one here, what we call borehole heat exchangers. So these are the two locations of the wells which were using before. You can add the plugin, and here we have three closed loop systems. So the closed loop systems are interconnected. You see, we have one array with total flow rates, inputs power of 260 megajoules per day. And this small diagram show you the connection between the different borehole heat exchangers. So we have one major inlet lines, and we distribute in equal parts the flow for the three BHEs, and then come back to the outlet pipe, and this is a closed circle. Okay, so that is then if we look the temperature distribution, so this example starts from a location where we have, or from a point in time where the open loop system, which I was modeling before, has been already operating for a number of years. So this is the one snapshot in time, and from this we are going to start a simulation for the close with both systems together. So here it's going to start happening something in these boreholes. We will see. So we will decrease the temperature in three locations, which I'm going to show here in the view after certain time. These calculations are numerically complex, so it's quite important to have discretization, well discretization around this. Now you see something is happening around the boreholes, and if I leave the simulation for a longer time, I will see. If I look at BHE inlet and the temperature history, I can see what is happening in all the inlet pipes. So I have three, and in all the three outlet pipes. So we started with a bit less than 10 because the calculation was already happening before. Since we started asking 260 megajoules per day of power, So we see that there is a decrease of temperature, about 8 degrees and 7 degrees in the other case. So this and the elongation of the heat plumes is certain tendency to go in this direction is because the flow direction goes also in the same way. So this another advantage of FEFLOW here is because originally the software is designed for groundwater modeling, so we have the full capability to simulate complex flow fields into FEFLOW. Okay, so before I can leave the simulation here open, and I see there are several names, several people already working with FEFLOW. So I'm going to show you as a premiere, so what is coming in the next FEFLOW version. So let me open the file so I can take the same example. So okay, so we open the file in the new version. Let's go here. Let's take this one. It's the very same file. So we go back to this well manager interface, and then it show me all the way. So this interface has been now extended. So you have the possibility here. These are the same boreholes that we have, injection and production, to create a group. We can say this is the group number 1, to give a name. And then if apply, I can apply some properties. So I have 2 multi-layer wells, and I have one array of 3 VHGs, so one group with 3 VHGs. So I can directly say I would like to apply to this group, which could be tens of multi-layer wells. I could connect it directly with open loop tool. So it's going to consider an open loop system for the wells directly from here. And in the case of the closed loop system, it recognizes there is an array, it's parallel, so you can define whether you want a parallel or serial. So you can basically have hundreds of boreholes directly in the table, and then with a couple of clicks FEFLOW, I want to connect these ones in parallel into a closed loop system, and FEFLOW creates all the connections. You define the flow rates, type of input for the energy or power, and the amounts, and then FEFLOW is going to calculate directly with this. So that's a really, it looks very simple in terms of changes, but it's a huge improvement for those who are working with geothermal modelings, because from one location you are capable to control all the information related for the open loop or closed loop systems. Okay, so back to the model. So the calculation continues, and we see that there is extension of the cold plumes in direction of the flow field. I will stop this. The second example that I would like to show you is another model. This time is a little bit more complex. So this model has been built entirely with FEFLOW and structure meshes. So for simplicity, I have a number of blocks. So I just let me plot this fault. So we have a number of faults. So let me deactivate this and show you. So we have 2 faults that are just crossing here into the system, and we have also some boreholes. So we have inclined boreholes. So let's switch off this. We have 2 boreholes inclined, and the boreholes it's a duplex. It's injection and production well. At the beginning of the simulation, we have simulated geothermal gradient, so 10 degrees and about 85, I think, is on the bottom of the system, or 86 on the bottom of the system. There is no flow for simplicity, and we start injecting or pumping. So to save some time, because I see a lot of questions. So this is the temperature what we see directly in the production well after injecting about 45 Celsius degrees. So if I stop this and come back to the well manager, again from the well manager, from one location, you control injection temperature directly here. So you can easily test this. So we are circulating about 1,000 cubes per day, which is actually quite a lot into the system. With this, I would like to thank you for participating in this webinar. Next month, we have another different topic of the webinar, so just stay tuned. Go to our website, Academy, the Academy by dhi.com, and you will see the current available webinars. If you're interested in learning FEFLOW for your projects, no, I will recommend you to come to Berlin and then have a discussion with us in 3 days, so you will learn everything related to geothermal modeling from shallow down to deep geothermal reservoirs. And with this, I would like to thank you for participating in this webinar, and I hope to see you the next time. Have a good day. Bye.